Yeah, so please take a seat. So we start this afternoon session with a review on data analysis techniques in high contrast imaging with Jean-Baptiste Ruffio from UC San Diego. So you can start.
Sound check. Can you hear me? Good. So yeah, my goal today was to attempt and most likely fail at giving an overview of data analysis technique for high contrast imaging. I've realized that we have a lot of different algorithms, a lot of different approaches, and I'm not going to be able to go through it all. But we'll try. First, thank you very much for inviting. I'm happy to be here this time. Last time in Leiden, I ended up stuck in my hotel room. I was by the train station in the Hibis Hotel, and Jerry Schwan had to give my talk, if I remember correctly. So it's good to be here this time. I was thinking, if I need to summarize data analysis or post-processing, I'm going to use those words interchangeably for high contrast imaging. I think the one word that comes to mind is speckles. So what are speckles? Where do they come from? So if you have a circular aperture, so I've been stealing those slides from Bruce McIntosh, so thank you, Bruce. If you have a circular aperture, perfect. You might know from Fourier optics, then your image of your star on your detector is going to be a nice airy pattern. But optics are not perfect. You might have polishing errors. They're not perfectly flat. They might be misaligned a little bit. If you take a Fourier transform of those phase errors, then you'll get a very speckly point spread function. If on top of that you're on the ground and you have variable atmospheres, then all of that has become like variable and it becomes really hard to detect faint point source next to bright star, which is what we all try to do. By the way, a note on speckles. Speckles is a very weird, I don't think I can actually define it. It's basically anything we don't like, and that's probably made out of starlight. I talk about speckles in raw point spread function like this, but I also talk about speckles in post-processing, like residual speckles. I'll also talk about speckles when you have wavy things in a spectrum. So it's one of those things that means nothing and everything at the same time. Don't worry about it. So the first thing we typically try to do, as you probably all know, is we try to build a chronograph. So the idea of a chronograph is we try to optimize a mask or a series of masks for the light to interfere destructively in a region of interest, which we call a dark hole. So this is, again, a slide from Bruce, the Roman chronograph, and you can see, I'm going to let it play one more time. When the mask is complete, you get that very nice dark hole and a little planet popping up on the right side. Unfortunately, here we go. Unfortunately, that's never perfect. There's also always going to be residual speckles, and that's why we need data analysis and post-processing. So then we need to apply some techniques, some observing strategy to try to disentangle the planet from those nasty speckles. So three main strategies that have been used commonly are angular differential imaging, ADI, spectral differential imaging, SDI, and one I didn't put here because like reference differential imaging is just you go to another star and then you do reference PSF subtraction like this. But starting with ADI, the idea, okay, it's a little fuzzy, but you might be able actually to spot there's a little dot on the left side of the video that rotates around the star. And that's because on a ground-based telescope, your sky actually rotates over time, but your field of view can be fixed for our typical telescopes. And the speckles are fixed in the telescope frame. So that will allow us to build a model of the speckles that we can then subtract. For SDI, it's a little different. We use the wavelength information. So at different wavelengths, the PSF, as you go to longer wavelengths, the point spread function, so all your speckles is going to scale outward. It's going to magnify your PSF, but the separation between the planet and the star is going to remain fixed. So again, one more type of diversity you can use to tell them apart. Carlos showed you this slide this morning. So this is the most simple algorithm you can use that was introduced by Christian Marois in 2006, 20 years ago. And this is the idea that if you have an ADI sequence, the simplest model for the speckles, you take a median of all of those, then you subtract that median image from all your individual exposures, then you can derotate them to realign the planet, and then combine them, and then you get a nice speckle subtracted image with the planet in there. In practice, we have way more sophisticated algorithms to do this. I'm going to get back to this. You have heard several talks this morning talking about this with machine learning and all that fun stuff. But this is a good illustration. Also in practice, we actually use different observing strategies together. We don't use only one of them. So this is an example of sequence from the Gemini Planet Imager, so GPI, which is an integral field spectrograph. So what that means is that we get both images and spectra at each position in this image. And I've just stacked all the cubes and plotted this as a movie. So you can see all the breathing here is the wavelengths changing. Then you might be able to spot there's a little point source on the left that actually rotates over time. And then, again, we apply some math, algorithms, and we get a speckle subtracted image. Those are not planets. This is a calibration field with a lot of background stars. And here I might mention that something that actually Christian taught me very early on is the fact that there's a difference between observing strategies and the algorithms you use to do PSF subtraction. You might use the same algorithm on different observing strategies or different observing strategies on with the same algorithm. So it's kind of important to maybe not mix them up too much. Once you have speckle subtracted images, we usually want to set some detection limits. So you might first, well, you have not done any flux extraction yet, so maybe one very quick step, which is not going to work very well, but if you convolve this with an aperture, that might help you extract the planet flux a little bit. But what we can do is draw concentric annuli around the star and compute the standard deviation of the noise in each of those annuli. That's going to give you a sigma, standard deviation. If you do 5 times that, then you can define a rough detection threshold. That's not a fixed detection threshold. You're going to have to pick your detection threshold based on your performance of your algorithm. So if your algorithm doesn't perform that well, maybe 5 is not enough. You might need to go to 7, 8. But that's part of the process. And with those detection thresholds, we can plot them as a function of projected separation, so the distance between the star and the planet, and as a function on the y-axis of the planet-to-star flux ratio. You might have heard of those curves as like contrast curves, but I've stopped using the word contrast about a few years ago because it became too confusing and I stopped understanding what it meant. So I only talk about flux ratio or detection threshold or sensitivity curves now. And this shows those for past, current, and future facilities, like some of them. I've took the liberty to just move JWST down a little bit because it does perform a little bit than this now. And what I found interesting when looking at this is the first planets we discovered were about 10 to the -4 in flux ratio. And if our goal is to detect exo-Earth around Earth analogs, then we need to go down to 10 to the -10. And right now, we're basically halfway through. We're at 10 to the -7 for ground-based telescope and JWST. Hopefully, Roman is going to get us a little further down. But a caveat that I wanted to mention on this slide, which I think has been mentioned before, but worth insisting on, is the flux ratio depends on which wavelengths you're looking at. JWST at 10 to the -7 at 3 to 5 microns, comfortably sensitive to the Saturn mass object. If you look at ground-based telescope at the same flux ratio, probably sensitive to a few Jupiter masses, typically. And in reflected light, it's a whole different story. So those are fully processed contrast curves. That means you have any hardware gain you had, like from your chronograph, and any post-processing gain you could get. One way you can think about it is you have that PSF profile, raw, unobstructed, no chronograph point spread function from your star, and you have some planets you want to detect. You might build a chronograph, dig a dark hole so you get a little further down, and then you might use some post-processing to get even further down. Actually, I've used the post-processing gain before, but I think it leads to potential like misunderstanding on the post-processing. Is that first, it seems like the chronograph gain and the post-processing gain are separable. They're not. Actually, Marcus mentioned that earlier, and I fully agree. They go together. The performance, what kind of instrument you build is going to constrain what kind of post-processing gain you might be able to get. And also, it doesn't show that there's actually a fundamental noise floor there, which is something I wanted to mention. In any system, for example, if you look far away from your star, you're typically going to be background noise limited or detect noise limited. It's going to be a flat limit. If you go very close in, you're going to be very often limited by the variability of your point spread function. So maybe your star doesn't fall always exactly at the center of your chronograph, or you might have some, like your optics might move a little bit, so your PSF is going to be variable. That's going to set a systematic floor. And then, of course, you have your photo noise from the star. That's at another floor across the board. And instead of thinking about the performance of an algorithm as what gain it brings, I think it's more informative to think about it like how close to that limit it gets you. A good algorithm is going to be one that gets close to those fundamental limits. And I wanted to mention that because I think we don't always think enough about how much room we have left for post-processing. And that's a lesson I learned from JetBrains-C, because for JetBrains-C it's really easy, it's much easier to get this fundamental noise floor. It's extremely hard to do from the ground, but I think it's worth doing. Another thing I wanted to mention is, again, what Marcos mentioned earlier, is the fact that what matters is really what you get at the end, not really how you got there, like the separation between how much starlight suppression you got from your chronograph system and how much you got from post-processing. So that's going to be relevant, especially at the end when I talk about data processing for NeurSpec, which you have heard already about a lot. But then in that case, if you don't have a chronograph, you need to work really hard in post-processing to detect your planets. So if you build a chronograph, then you might work less, like you don't need to work as hard maybe in post-processing, but there's no free lunch. If you have a chronograph, then you're typically going to lose throughput, especially close in. Like someone mentioned for AFLEP, like 7% throughput close in for JetBrains-C. So it's going to be a trade-off. You certainly don't want to fully to minimize your dark hole as deep as you can if you pay the price elsewhere. Right. So another thing I wanted to mention about data analysis is I think often we think of it as just speckle subtraction or PSS subtraction, but it's actually a lot more than this. Nowadays, I think about data analysis as everything, like the bridge between your raw detector images and your planet properties. And often you're going to start with an instrument pipeline. So you might have your typical detector calibration steps. You might have dark subtraction, flat fielding, maybe 1/f noise correction, more complicated processing steps like fringing. If you have an integral for spectrograph like GPI, then you're probably going to want to build spectral cubes to go from those hard to read like spectra on your detectors to a nicely sampled cube. Then you can do your speckle subtraction. That I think most people are familiar with this, but that's going to depend on your observing strategy. Then we're going to need to do flux extraction or spectral extraction, which is tricky by itself because you tend to distort your planet signal in a lot of weird ways. Then you'll probably want to define a likelihood or a chi-square, and for that you'll need a noise model. Is your noise Gaussian? Is it not? I know a lot of, like some of you have thought about cases where with non-Gaussian noise, you're probably going to want to have your covariance matrix when you extract spectra. I'll get back to that later in the talk. You'll need atmospheric models, and all of that is data analysis. And the reason I want to highlight all those steps is how good your data analysis is. It's going to be as good as the weakest link in here. So you don't want to focus too hard on any one step if you're limited by another step. Actually, I thought it was really interesting this morning from like the Amigo algorithm. That's, I think, that idea that something else might be limiting you. In that case, you might want to work on that. Nowadays, I think the instrument pipelines could use a little more love in general, but. Okay, so what are the typical challenges of PSF subtraction or speckle subtraction? I think the first one, again, has been mentioned this morning. It makes my talk a little easier, is this idea of over or self-subtraction of the planet signal. So this is a plot from Laurent Perriot's paper in 2016. So if you start on the left with just a section of your image with a bunch of speckles everywhere, and you apply some speckle subtraction techniques, then at the like in the middle of the crosshair here, you're supposed to have a point source, but you can see it's very weird. There's like negative lobes and positive lobes. It's all like distorted. And that's because the algorithm used some speckles to over-subtract your planet, effectively. Even the planet might self-subtract its stuff. I'm not going to get into the math. But there's many ways you can try to deal with this. So Laurent showed that you can forward model this, but I think anyone that has worked on data analysis over the past 10 years had to address this in one way or another. But there's different ways to do this. The other challenge is how you model your noise. So this is an image from the NURCAM chronograph. See, it's messy. The noise is not uniform. And that's an assumption we often make. For example, when I say that we estimate the noise in concentric annuli by just computing standard deviation, that assumes your noise is uniform at a given separation. And it's usually not. So it's going to impact your false positives. So again, I think all the people that have worked on algorithms for the past 20 years, that's something that I've had to tackle in some way. So yeah, Collis already kind of did this, but I thought I'd put it in more of a timeline slide. So from the classical ADI in 2006 to now 20 years, and I thought I would just highlight some of the milestones. I'm sure I missed a lot of papers and algorithms, so please let me know, and I'll add them for the future. But probably the first important step was low-key. So this idea that instead of doing a median, you can do a linear combination of images that gives you more flexibility and to account for some of the variability of your point spread function. And that allowed the detection of HRS-99 in 2008. Several years later, you had this idea of principal component analysis, or CLIP, which are words you might have heard, but I don't know if everyone necessarily knows what they are. The idea of principal component analysis and CLIP is if you have 300 images, they're all very noisy, so you might not want to do a linear combination of 300 noisy images. So principal component analysis basically builds a smaller basis of maybe like 30, 20, or 10, like that's a number to be determined of modes, of principal components. And that's going to make your algorithm a lot more stable. I'm not going to get into detail. But turns out, Dmitry Savransky also showed us in 2015 that all of those algorithms are basically the same. If you do low-key with some regularization, PCA, or CLIP, they're just different words for exactly the same math. So don't get too worried about all the names everywhere. Very often, they actually refer to the same thing. That doesn't mean that every implementation is the same, because everyone makes decisions when they implement them that makes them better or worse. But anyway. In 2014, you had the small sample statistic paper from Dimitri Maoué. What that paper showed is when you define that analysis and you compute the standard deviation to get your detection threshold, if you get really close to the star, then you have very few samples of your noise. And that makes it difficult to actually estimate your standard deviation. And you're going to make an error, and you need to account for it. Otherwise, you overestimate your sensitivity. And that can go up to an order of magnitude. So it's pretty important to take into account. 2015, paper with Faustine Cantaloupe, Andromeda, started something a little different, basically forward modeling that distortion of the planets. So if you think about taking the difference of two images that are rotated from each other, then you'll have a positive planet and a negative planet, but that's fully predictable. So you can model that and look for that positive, negative signal and write an algorithm that doesn't work very well. Laurent worked on the same idea, and myself as well, but applying that idea to CLIP, so it's a little more challenging because now you have to forward model the planet through the principal component calculation. If you love linear algebra, it's a great read. If you don't, I don't recommend it. But I love it. 2018, PACO, again, something a bit different here than the other algorithms. The idea of PACO, as I understand it, so you define your covariance matrix from your data. And what I really like about this algorithm is that you jointly fit the starlight and the planet together and worked extremely well. Lots of paper. Some of them I only discovered recently, but like great algorithm. in 2018 is also when started working on machine learning and neural networks. So Carlos Gomez-Gonzalez started working on that kind of approaches. We heard like SpeckleNet earlier this morning as well now. And I'm not going to lie, at that point, I no longer understand all those algorithms. So I'm glad you all talked about them this morning so that I don't have to. Thank you very much. But there's been a lot of progress, and obviously it's confusing. Just ask your local like data analysis expert. They're probably going to help you find whichever algorithm is best for you. I wanted to highlight some community effort. So it's really hard to compare different algorithms because your contrast curves, your sensitivity curves, they don't necessarily represent the amount of like, well, they give you a detection threshold, but they don't tell you how much false positives you might get for that detection threshold. So it becomes really hard to compare different algorithms apple to apple, and that's what was attempted in this work. So it also provides a data set, like publicly accessible, where anyone working on algorithms can try to reduce it and compare it to all the other algorithms that people have submitted. So I think really good effort. There have been different phases to this data challenge for some planet detection and planet characterization, and apparently the next one is going to be disk imaging. Just wanted to highlight this. So far, I've mostly been mentioning algorithms that tackle the typical strategies: angular differential imaging, spectral differential imaging, reference differential imaging. But there's a whole landscape of different observing strategies. We have heard some of them this morning, like current differential imaging, or like the focal plane reconstruction telemetries with Vertigo's talk. I obviously can't go through all of those. Any of those observing strategies would need their own timeline and talk. I mean, let's just think about like interferometry with gravity, amazing, but it's not your typical PCA low-key clip type thing. So, and I think we're doing a lot more of like a diverse set of observing strategies these days, which is really great. If you think detecting planets is hard, good luck for the people doing disks. They're extended sources, so they get distorted in all the weirdest way you can imagine. So I don't envy, but kudos to people that get this to work. I think Riley is going to have a talk talking about disk later, so I'm going to defer to her. Another goal of data analysis is not just to detect your planets. I mean, one thing we really care about is characterizing their atmospheres, extracting spectra. And you might have found yourself like given different spectra from different instruments or different epochs, and then they don't match. Well, welcome to the club. This is hard. This is hard. There's always going to be residual correlated noise in your spectra, and we need to model those. So just to highlight the issue here is so a data cube, speckle subtracted from GPy showing 51 Eri. 51 Eridani B, so 2 Jupiter mass planet-ish. And you can see the background, like the bubbling background. That's not your white noise. That's not your photon noise. That's just residual correlated speckle noise. And if you don't account for it when you fit your spectra, then that's going to bias your atmospheric inference. You're not going to get the right answer when you measure your composition, your effective temperature, your surface gravity. It's really important to take into account, and that's what Greco and Brand in 2014 really highlighted. That paper doesn't have enough citations. It has like a fifth of the citation of the small sample statistic paper. This is not a fifth less important. So if you extract spectra, make sure you also extract covariances. And if you're someone like fitting models, make sure you ask the person that did the data analysis for a covariance matrix. Yeah. Another way to visualize the effect of that correlated residual speckle noise is by plotting power spectral density. So I stole this plot from Rico Lendman's paper, where he plotted so power spectral density. If you're not used to this, think about this as just information content as a function of spectral resolution. So here for 3 different molecules, water, carbon monoxide, methane in color. Your photon noise or your detector noise is what we call a white noise. So it's going to have a flat power spectral density. but speckle noise is going to dominate at low spectral resolution. So if you are speckle noise dominated, then actually you might benefit from going at slightly higher spectral resolution, maybe moderate spectral resolution. Obviously, if you go too high, then you start to get hit by your detector noise, so that's going to be a limit. But that's going to be my transition sort of to the last part of my talk, which is to discuss more like moderate and high spectral resolution, although I'm going to focus primarily on JRC NERSPEC, because that's what I've been working on for the past couple of years now. So I think the seminal papers for moderate resolution spectroscopy or high resolution spectroscopy were the paper from Quinn Konopacki and Ignace Snellen. So Konopacki 2013 was using OSIRIS at a resolution of 4,000 to detect water and carbon monoxide in the atmosphere at HRX 99C. So the idea of higher resolution spectroscopy is you can use atmospheric template, so or molecular templates, like water, carbon monoxide, methane, cross-collate them with your spectra. So that means you shift your template with different radial velocities, and you look at how well it matches, and then you plot that correlation function as a function of radial velocity. If you see a peak, it means you detected either your planet or your molecules or whatever you were interested in. So Snellen in 2014, same idea, same kind of techniques, but much higher spectral resolution with cryo-RS, I think 100,000, able to measure the radial velocity and the orbital spin of, the rotational spin, sorry, of beta pictoris b. If you have an integral Swift spectrograph, you can use that to highlight the position of, to disentangle the signal of the planet from the signal of your star, because the spectrum of the star doesn't look anything like the spectrum of your planet, with algorithms like molecular mapping from Jens. So this is, again, detection of beta pictoris b, carbon monoxide and water template from Symphony, I think resolution of 5,000-ish. And at this point, I'm basically going to have to skip about a decade of development and progress from moderate and high resolution spectroscopy from the ground. There's a few talks this afternoon on KPIC, high-rise. Hopefully, we'll talk about some of those things. But the thing I want to highlight is all the results that we're getting from JRC today have leveraged all the lessons learned from the ground, and we didn't get there in a day. So you might remember those results that Jerry presented yesterday on HRX 99 with JRC NERSPEC. So JRC NERSPEC is also an integral Swift spectrograph, has a moderate resolution spectroscopy mode at an R of about 3,000. It does not have a chronograph, and so originally, I think we thought that we were not going to be able to, high contrast was going to be tough for NERSPEC. And when Chaz and Klaus invited me to join to work on those data, the program only targeted HRX9B and HRX9C because we thought that E and D were going to be too hard. We were like, we think we can do a little bit better. Let's look at all the planets. And I'm glad we did. So how do we do this? I'm going to try to get into a little bit of the detail of the data analysis for this. What I wanted to mention is NERSPEC nowadays, I think Marshall mentioned that any planet that can be seen with a chronograph, we can get a spectrum of. Sort of what's highlighted here, all the approved program, a lot of the data we already have, some of the data is coming. But yeah, approved NERSPEC program for the directly imaged planets highlighted in black. So yes, NERSPEC is an integral Swift spectrograph, like I mentioned before. That means at every position we get a spectrum, but it's a slicer integral Swift spectrograph. So that means that the field of view is divided in 30 slices. I like to think about them as slits. If you're familiar with slit spectroscopy, this is just 30 slits next to each other, and they're just organized on the detector on top of each other. And then each slice is dispersed horizontally so that you get the spectrum for every slit on your field of view. So, and you have 2 detectors for NERSPEC. Now, if you take that data, use the instrument pipeline, and build a cube, a spectral cube that's regularly sampled, you'll actually get spectra like this. And some of you who have used NeurSpec might have seen those kind of oscillations in spectra. If you're trying to detect a planet that's 100, 1,000, or 10,000 times fainter than the speckles, and you have systematics like this that are variable between the different positions, well, you'll have a hard time. So, but I want to remind you something I said earlier, which is when you think about data analysis, it's going to be as good as the weakest link in the process. So in this case, well, what we need to understand is where do those come from, the systematics? And they're actually an artifact from the data processing. The cube or reconstructor was an algorithm called Drizzle. Effectively, that's what's creating the oscillations. I'm going to try to give you some intuition of where that comes from. So you have an image of the detector on the left. I zoom in on one slice. Again, that's basically a slit spectrum. You can see that there's some curvature to that trace. So a planet or a star, a point source, is going to follow, for example, the red highlighted region here. That would be the trace of, so the spectrum of a point source. You can see it crosses different detector rows. So what that means is, at some wavelengths, the flux of the planet is centered on a pixel, so you're going to have a high flux. But at some other wavelengths, it's going to split between two rows. So your flux is going to be lower in any given pixel. And then periodically, you're going to get high and lows in your fluxes. And in the cube reconstruction, that's not accounted for. So those ups and downs in the flux, you'll get them in your extracted cubes. So basically, the path forward was like, well, let's not build a cube. Let's just work in detector data only, because there's actually no oscillation in the detector data. So that's how we get those images where, but I'm going to go slightly deeper in the data analysis on the next slide. But what I want to explain is how do we get from those raw star images to a nice signal-to-noise ratio map where you can detect very faint companion next to bright stars. So go back to that zoom in of the detector on NeurSpec. If I take a horizontal cut of the detector, and I plot the flux of all the pixels, you get the top panel over there. So although ups and downs, mostly speckles, mostly starlight, you can see that where my orange cut crosses the red area, you see like sine waves. That's your carbon monoxide. And I love to highlight this because you didn't do any data processing yet. You've just literally plotted your pixel intensity on your detector, but you have already detected a companion, because the only way you can get those features is from carbon monoxide, and there's no carbon monoxide in that star. So what we ended up doing is build a model of the planet using a WebPSF and an atmospheric model that we project on that detector. So we have the x, y, lambda coordinate of every pixel on that detector. And we also build a model of the starlight, so that for that we have to derive an empirical model of the stellar spectrum. I can't get into much more of the detail of this, and then we use a spline model that's very flexible that can model any continuum in like the variations of the continuum for the starlight. We jointly fit them, and that means that every position of the planet we can fit for the planet flux, get an error bar on that flux, and from that, if you take the flux divided by the error bar, you get an SNR map, and that's how we get all those detection maps. So each panel, different system with the unprocessed star and your detection map. Just more, and this is from Emily's program, just to show you that this is no longer something we have done on one system, and Alex has done a good job like automating this and reducing data as they come. Very quickly, I wanted to mention that although that forward model is amazing, it works extremely well for planet detection and like plotting contrast curves. It does not give you a spectrum. So, and for atmospheric characterization, it's so much easier if you have a 1D spectrum. It makes your life a lot simpler. So when we extract high-pass filter spectra like this is not a forward model. So what we end up doing is high-pass filtering the data directly in the detector images. Then we have to combine them all, and we do some flux extraction. I'm going to skip on the details here. But just wanted to mention that those are not forward modeling in the same way that I just described earlier. So yeah, this is from Emily's program again. Okay, so in the last few minutes, I just wanted to say a word that if we started from a movie of the HRS 9 planets, I think one of our goals that a lot of us are working on is trying to aim for getting a movie of a solar system analog eventually. Oh, sorry, I didn't start the movie actually. Yeah, this is animation by Corey Spohn. Great simulation. And we have been thinking about applying the lessons learned from NERSPEC to the Habitable World Observatory, so HWO. So because there's going to be similar issues. So if you look at the oxygen spectrum of an Earth analog, and if you plot it as different spectral resolution, so 140, which is a number you might have gotten, that's quoted a lot for typical HWO. So you only get one dip. But if you go to higher spectral resolution, then you can start to resolve the actual oxygen features. And so you'll get potentially a lot more information that you can leverage to disentangle the starlight, the exozodi, and other things. So I have a paper that's submitted, that's in review, where we look at, where we simulated exo-Earth observation around 100 plus stars in the solar neighborhood. And for given exposure time, trying to see what the distribution of SNR of the oxygen detection using template matching as a function of spectral resolution. And what we found, I mean, there's no definitive answers because we don't have final assumptions, but it seems like potentially a higher spectral resolution, 1,000, maybe above, could be hypothetical, but could be more optimal. On this note, so these are some of my takeaways. Data analysis is not just subtracting speckles or modeling speckles. It's everything from your detector to your planet properties. And you really need to be careful. Try to think about, have an overview of all the steps that are involved in your data analysis. There's more than ADI, SDI, IDI as observing strategies. I mean, I think gravity, moderate high resolution spectroscopy, coherent referential imaging, combining Gaia, RV, combining multiple epochs, all of those really exciting avenues. Think about what is your systematic and your noise floor in any of your observations, because that's going to define how much harder it's worth, is it worth it to work harder to get more gain from your data analysis? Or are you there? Or are you already at your photo noise limit? I didn't go in any detail in any of the paper over the past 20 years, but hopefully, and with the talks this morning, hopefully you understood there has been major progress over the past 20 years. We're doing a lot better now. I mean, Mark was showing detecting planets from 2011. So there's surely a lot more progress to come on this front. Wanted to highlight again a reminder to really compute your covariance matrices when you extract spectra and share them with anyone doing the atmospheric modeling if it's not you. And last but not least, read that idea that instrumentation, observing strategies, and data analysis are not separable things. So for example, sorry, I mean, we've been talking about it a lot, so I apologize for this, but yeah, NERSPEC, really amazing example where without a chronograph, we reach the same kind of starlight suppression just from pure data analysis, just because it has a 60% bandpass, 5 times the throughput of NERCAM, and the spectral resolution allows us to go have a factor of 1,000 and hopefully in the future 10,000 in starlight suppression. So I think I had 1 more minute, but that's it for me.
Okay, so we have a lot of time for questions.
I have a question for this exo-Earth case with HWO. So getting high-resolution spectra is really great if you have a lot of photons. Is in the case of HWO, is there enough light to take such high resolution spectra to do that? Or do we need a larger mirror to actually utilize these techniques?
Short answer, I think yes. And the thing is, I don't actually think the photons of the planet are the important thing. What's going to be your limiting factor is the photon noise, usually from the star, the exozote. That's going to be your noise floor. So that's the thing that's going to be relevant when you think about high spectral resolution, not the number of photons from the planet. So yeah, we found it. And I mean, if you integrate for 400 hours or like 700 hours, you do get a significant amount of number of photons.
This is a great talk. You said that the star spectrum doesn't have any CO in it, and that's, I think, true for a lot of the systems that we're working on that
Yes.
are early type stars, that are giant planets, you know, those form preferentially. For something more like, say, EPS-ARI, which is a K-dwarf, you know, has lots of CO. Does that become problematic, or you know, is the temperatures of the CO different? Is that enough? Is the spectral resolution enough?
Yeah, I mean, this is an excellent point. It's not problematic, but it's manageable. The thing is, because it's an integral spectrograph, you have basically all your field of view is just pure starlight. And you can use that information to get an incredibly like high SNR spectrum of your star. So you know exactly what the star should look like. Even if it has some CO features, you basically have a perfect template, give or take, of your star. And so any deviation, I mean, even if you have some CO on the star, the CO feature of the star are not going to look like the CO features of your planet. And also, I mean, you're going to have other things in your planet that are not just CO. So at least with JWST, that's working okay. A good point.
I do have a question. Can you comment on the issue of continuum reconstruction?
Yeah.
And whether this is important or not?
I actually had some slides, but I had to take them away. So we are working on it for JWST. So far, basically the data analysis is going to be different depending what your goals are. For computing SNR map planet detection, that works very well. Extracting high-pass filtered spectra, that works pretty well. We get really good results. Doing PSF subtraction with JWST, we're still struggling because it's definitely an spatially undersampled instrument. So we have, if you do simple linear interpolation to like align your reference star with your science, then you're going to be limited by interpolation errors. And so unless you have a very low contrast target, like think about 1-to-1 planet to speckle ratio, and in that case, you can get the continuum. Otherwise, we still need to work harder. But I think it's going to be possible. It's just going to take time. Okay, that's my, sorry, short answer, possible, will take more time, certainly important, but also not mandatory for a lot of science cases too.
Julian Girard, Space Telescope. So, yeah, I wouldn't want to be doing that. Kudos to the people that do that. I heard that before. Anyway, no, it's amazing. I was thinking, you know, IFUs are known to have issues of, you know, stray light and saturation and, you know, other effects, and also like, you know, a lot of times they don't have a chronographic mask in the focal plane. So if you could influence the design decisions for future IFUs for hub worlds, for example, you know, what would be your recommendation to basically help with that? And
I mean,
even though you get rid of all the, you know, stray light and stuff with those techniques, you know, you still have to cope with photon noise, right?
Right. I mean, first, like, let's try to build a NIRSpec with a chronograph. I mean, I'd be excited about that.
Yeah, just like one-on-one, you put a mask, yeah.
I know we keep saying that NIRSpec doesn't have a chronograph and can do high contrast, but what that shows is not that we don't need a chronograph. What that shows is like how incredible would it be if we had an optimized chronograph for that instrument that would do incredible things. So maybe that's one. Second one is that maybe make NIRSpec be able to do target acquisition on a slightly brighter star than 11 or 12 mag. because, yeah, we saturate in, most of the directly imaged host stars will saturate in 2 reads. So that's why in a lot of the SNR maps that I've showed, you have like a bar. That's not a chronographic bar, it's just that it saturates, and so we lose a whole bar in the field of view. So certainly it would help, and a chronograph would help with that, absolutely.
One more? No? Okay. Yeah, short. Okay, short.
Thanks, JB. I actually have a sort of follow-up question to Julien's, which is if we kind of think forward to future facilities with higher resolution integral field spectrographs, basically how much can we leverage in terms of the diversity between stellar spectra and planetary spectra if we're beyond R of, say, 3000?
I mean, you can leverage more things. At higher spectral resolution, science cases that I get excited about are like radial velocity, examoons, like trace species, isotopologues, spin broadening. Those things you can't do at moderate spectral resolution typically. I don't know, does that answer your question? Or? I was thinking more algorithms, but yeah. Sorry? I was thinking more like algorithms, like the application of this technique at higher spectral resolution. Yeah, I mean, those are the same techniques we use on CAPEC or other things. So that's what I meant by this is leveraging all the work we've done on the ground. Same algorithms.
Okay, so I think we should think again, Jean-Baptiste.